Hello, today we study limits at infinity. But firstly, I think you would ask me, why do we do limits again? Right? Because we did limits in the very first chapter of this course. And we finished the second chapter and we are almost at the end of the third chapter. And we go back to limits. And now limits at infinity. Look at this. We study limits at some point, right? Because we want to understand the behavior of some function at some point. Is that correct? For example, we learn this limit when x approaches 0 from the right or x approaches 0 from the left, right? The first one is infinity and the second one is negative infinity. The limit of 1 over x at 0 does not exist because the left limit and the right limit are not equal. But one side limit exists, is that correct? So these two limits just tell us about how the function behaves at 0. Does that make sense? No, that is very important for us because we want to know that. Agree? And from these two limits, we say actually the point or the straight line, not the point, x equal to 0 is vertical asymptote of this function. Right? Vertical asymptote. So when you consider some point and the limit at that point, at least one side limit at that point is infinity, that straight line, that vertical straight line, let's say that is vertical asymptote. That means the graph just approaches, right, that straight line, but never intersect with that straight line. And so we use that information to graph the function. Do you remember that? We use that to graph the function, very brief graph. Until now, we don't do that, in detail, but we know exactly. In order to graph 1 over x, when x greater than 0, so when x approaches 0 in here, this is 0, the function just go up, right? So, you have something like this. Is that correct? That is the part for x greater than 0. For x less than 0, so you have another one right here. Not exact, but the graph of 1 over x looks like this. All right, now look at this. The function is defined everywhere except 0. You see, that is the domain of 1 over x. That is the whole number line exclude 0. And when you consider this function, you might ask yourself, what happens if x approaches infinity? That means you are interested in the behavior of the function at infinity, right? Behavior of the function at infinity, positive or negative infinity. So that means you need to consider the limit of the function when x approaches infinity. Is that correct? Then you need to consider the following limit: 1 over x when x approaches infinity or x approaches negative infinity. And this function is pretty easy, right? The limit is 0. Why? Because 1 divided by a very big number, you increase m, right? So the inverse of that number should be, decreased to 0. That's it. So the limit is 0. Again, what does it mean? If you look at this from the point of view of asymptotes, that is the graph of the function, right? The graph of the function in here when x approaches positive infinity in here, just closer to the y equal to 0. Is that correct? To the y equal to 0. This is y equal to 0. The x-axis is the y equal to 0. And in this case, y equal to 0 is horizontal asymptote. This is horizontal asymptote. You see, we learn, behavior of function at some point. If the limit as that function is x, right, and a finite number, so we don't have vertical asymptote over there. Do you remember that? Because that discontinuity is removable, right? But if that discontinuity is not removable and the limit, one side limit at least, equals infinity, so we have vertical asymptote. And now, if the limit of that function at infinity is a finite number, then that horizontal line is horizontal asymptote. So basically, vertical asymptote, as you know how the function behave as some finite number, right? As some finite number. And now vertical asymptote and horizontal asymptote. That is the behavior of the function when x approaches infinity. That's why we need to study limits at infinity. Agree? Now let's move to definition of limits at infinity. We have that right here. Let L be a real number. We say the limit of the function equal to L when x approaches infinity. That means for each epsilon greater than 0, there exists a number m bigger than 0, such that the difference between fx and L is very small whenever x greater than m. You can see that right here. In this case, 0, right? The limit at infinity is 0. You see? 0 in here. So what does it mean? That means, you just increase x, right? X is right here. You just increase the x, right? Whatever, you have epsilon, very small epsilon in here, you might find, a number x. You might find such m, right? Which is m right here. So that for any x bigger than m, x bigger than m, the distance between, the function value and that number and the number L is less than epsilon. You see this? It's less than epsilon. So basically that is right here. So you fix for fixed epsilon, you may find a number m right here, such that for any x greater than m, means from the right of m, the distance from the function value to that number. In this number is not the x, right? This number is the y-axis, so that is y equal to 0. You see that? So this distance is less than the distance epsilon. So that is the meaning of limit at positive infinity. At negative infinity, you also have almost the same situation, right? Look at this. So you fix some epsilon in here. You might always find some number m. But since you consider limit at negative infinity, so you find some number m in here, such that for any x less than m, in this picture x is bigger than m, but in this x is less than m, right? Because we consider limit at negative infinity again. Then the distance from the function value to the y value in here, right? In this case is 0, is less than epsilon. So in that situation, we say yes, the limit of function at negative infinity is L. Does that make sense? And in this situation, in one of these situations, the y equal to L is called horizontal asymptote of the graph of the function. Does that make sense? So, in order to find a vertical asymptote, you just need to find points where the limit, one side limit at that point is infinity. But in order to find horizontal asymptote, you need to find the limit of the function at infinity. Okay, so let's consider some examples. The first example looks like this. You have function fx equal to 2x minus 1 over x plus 1. Let's find all asymptotes of this function. Okay. So I'm talking about vertical and horizontal. Okay. So just repeat that. That's fine. Because we need to understand the behavior of function at some point, right? When the function close to infinity, and what happened with the function when x close to infinity. So for vertical asymptote, you need to find all x where the function is not defined. So basically you need to solve this equation, x plus 1 equal to 0, and then that is x equal to -1. But that is not all. You need to consider the limit of the function at this point. Does that make sense? Make sure that the limit is infinity, because as I mentioned previously, this point is the point of discontinuity. But is it removable or not removable? If that is removable, so we don't have vertical asymptote. But if it's not removable, unremovable, so this is vertical asymptote. And it's pretty easy to see, yeah, the limit of this function when x approach -1 from the right, for example, is if this is from the right, so x plus 1 is always positive, right? But 2x minus 1, I would say like this. I hope you still remember this situation. I would think, yeah, that is similar to the case like limit of -3 over x plus 1 when x approaches -1 from the right, and that is -infinity. So yeah, this is vertical asymptote. Okay, now let's talk about horizontal asymptote. In order to do that, you need to consider the limit of the function at infinity. The limit of 2x minus 1 over x plus 1, x approaches infinity. Alright, look at this. So you might solve this problem in different ways. Let me show you how the textbooks show you, okay? And then I'll tell you another idea, which is very, similar, or we may say, yeah, that is equivalent idea, but in another form of expression. So in the textbook, they say, in order to solve this limit, I just pick, a term with the highest degree in here, but you have x to the 1 and x to the 1 in here, right? So you divide the top and the bottom by x. You have the following one. You have 2 minus 1 over x divided by 1 minus 1 over x, because you divide the top and the bottom by x. And since a limit of 1 over x at infinity is 0, right? Then this limit is nothing but 2 over 1, which is 2. So the limit of this function at infinity is 2. Does that make sense? Then y equal to 2 is horizontal asymptote. That's it. All right. If I solve this problem, I will do in the following way. And this idea is also important. Okay, I'll tell you, you can apply this idea each time when you solve such limit at infinity. So you look at the top and the bottom, they are polynomials, right? We have polynomial divided by some polynomial. And of course, what is the degree of your polynomial? The degree of the top is 1. You see this? In here you also have 1. Is that correct? So, the term with the highest degree in that polynomial will decide the behavior of the function at infinity. Understand that? Because if you between 2x and 1 does not decide the behavior of the function at infinity. That is only 2x. Does that make sense? So, when I consider the limit at infinity, I don't care about terms with lower degree than the degree of the polynomial. So I pick the term with the highest degree. And so the limit of this function is equal to the limit of 2x over x when x approaches infinity. Does that make sense? I just, ignore negative 1 and 1 because they don't affect on the behavior of the function at infinity. And that is just 2. Agree? I accept this solution. Does that make sense? But I really want to see, this small discussion in your solution. It tells me, yes, actually you understand at infinity 2x minus 1 is similar to 2x. Means two functions are similar. Does that make sense? At infinity, don't forget that. That happened only at infinity. Now look at these 3 limits. And let's use the idea of similarity we just discussed to solve these 3 limits. And you will see something very interesting. Alright, so for the first limit, I write in here that is the just limit of 5x over 3x squared when x approaches infinity. Because, we ignore 1 and 2. Okay, so this is equal to limit of 5 over 3x when x approaches infinity, and that is just 0. You see, it's pretty simple, right? Of course, you can solve, by the way, like you divide the top and the bottom by 1 over x squared. But you see that in the textbook. Right now, we may use similarity at infinity. Don't forget, right? At infinity. So, how to solve the second one? That is limit of 2x squared over 3x squared. X approaches infinity. And that is 3 over 2. Right? What is the last one? Limit of 2x squared over 3x cubed. X approaches infinity. That is limit of 2 over 3x. X approaches infinity. And that is 0 again. Let's do one more example. Let's choose 3x cubed plus 3x squared plus 1 over 100x squared plus 100. Okay, 1000, that's fine. When x approaches infinity. So we pick terms with the highest degree. On the top I have 3x cubed. In the bottom I have 100x squared. X approaches infinity. Right? I just ignore 3x squared plus 1 in here. Because again, right, at infinity the term x cubed will decide the behavior of the function. Because x cubed approaches infinity faster than x squared. So 3x squared plus 1 do not affect on the behavior of the function. Then we simplify x squared. We have limit of 3x over 100 when x approaches infinity. and that is infinity, right? Because 3 over 100, just coefficient, you take that out. And you have limit of x when x approaches infinity, that is just infinity. All right, so look at this 4 examples, especially the first one, the second one, and the last one. You may see something interesting. In the first limit, the degree on the top is 1 and the degree in the bottom is 2. You get 0 at infinity, right? I see the degree equal to 1 on the top divided by some polynomial of the degree equal to 2. So 1 less than 2, and that you get 0. I write here because 1 less than 2. Okay. In the second, you get what? You get 2 over 3. What is 2? 2 is the coefficient of this term. Is that correct? And 3 is the coefficient of this term. And the degrees of these two polynomials are equal. So that's why the limit is equal to just, fraction of the coefficients. Just the quotient of coefficients. Is that correct? So this happens when the degree, I can say, yeah, degree equals. Okay, degree equals. So in that situation, you have coefficient divided by coefficients. Does that make sense? And in the last one, you have infinity because the degree on the top is bigger than the degree in the denominator. Does that make sense? So that's why you get infinity. You may use this, in the future. Agree? If you see some polynomials divided by a polynomial and you need to consider the limit at infinity, please use this. You just need to consider, the terms with the highest degree. Does that make sense? That is enough. Okay? Now let's use this idea for more complicated functions. So suppose you need to find the limit of this function. When x approaches infinity, means positive infinity, right? So how to find this? Or, this limit helps us to find horizontal asymptote. Is that correct? Okay, now you know that, we need to use limit to find asymptotes, okay? So we use similarity. I write this limit is just 3x over square root of 2x squared. X approaches infinity. I already ignore -2 and 1, but we still need to work with square root of 2x squared. X approaches infinity. Positive infinity means x bigger than 0. I especially emphasize this because square root of x squared is absolute of x. Don't forget that, right? That is not x, that is absolute of x. But when x greater than 0, absolute of x is equal to x. Right? Because absolute is x if x greater than or equal to 0. And negative x if x less than 0. So that's why in this case you have limit of 3x. Here I write square root of 2, right? Absolute of x approaches 0, infinity, and that is the limit of 3x over square root of 2 times x approaches infinity. You simplify x, you get 3 over square root of 2. So, the limit of this guy is 3 over square root of 2. And that means y equal to 3 over square root of 2 is a horizontal asymptote. Okay? Now look at this. That is just limit at positive infinity, right? So what happens if we consider limit of the same function at negative infinity? You see the difference in here. All right, so again, I use similarity. I get 3x minus 2 over square root of 2x squared. X approaches negative infinity, right? And what we just discussing here, you see, this limit is equal to limit. I'm sorry, here we don't have 2. Okay, I just erase that, please. Limit of 3x square root of 2 in here, and then absolute of x. But what is absolute of x? That is negative x. Because x approaches negative infinity, which means, x less than 0. So absolute of x in this case is negative x. You see? So I have, this is limit of 3x divided by square root of 2 times negative x. X approaches negative infinity. You simplify x, you get 3 over negative square root of 2. Or you can write, negative 3 over square root of 2. So this function, 3x minus 2 over square root of 2x squared minus 1 has 2 horizontal asymptotes. You see, that is plus minus 3 over square root of 2. Does that make sense? So that means the graph of this function may look like this, I don't have exact graph of this, right? But I might guess. That this 3 over square root of 2. This is negative 3 over square root of 2. This is horizontal asymptote. This is horizontal asymptote. And when x approaches negative infinity, so the function approaches to this. You see? So negative infinity is right here. The function approach to this, so I might have something like this. Right? That is the behavior of the function at negative infinity. You see? Something like this. And, when x approaches positive infinity, so I have the following picture. And what happening here, I don't know. We need to analyze using the first and the second derivative. Does that make sense? So see, actually, limits at infinity helps us to find horizontal asymptotes again, right? And of course, using that, you may understand the behavior of the function at infinity. Suppose you consider this function, right? You consider this function. And you take the first and the second derivative, right? And you know where the function is increasing, decreasing, convex or concave. And suppose that you don't find the limit at infinity. In that case, you don't understand the behavior of the function at infinity, right? And suddenly, you may graph the function like this. Does that make sense? So that means you have a wrong graph. Because, graph never go above this straight line. Or never just pass through, this straight line. You see that? Because these two straight lines are horizontal asymptotes. Agree? In order to finish this video, let's consider one problem with trig functions. Okay? So, we have function psi x. Let's consider the limit of this function at infinity. So how do you think about that? The limit is x or not is x? Okay, so if you remember the graph of the function psi, right? So how does it look? Okay, so the psi 0 in here, let me see, that is pi over 2. That is 2 pi, that is pi, 3 pi over 2. Pi over 2, you go to 1, right? Okay, let's say this is 1. 1 should be less than, okay, let's say this is 1. 1 right here, and this is -1. Okay, so you have this, you have 0 in here, and then go down here, and then go up, right? And then you just continue that. And here you have almost the same. So what happened with this function at infinity? You don't know that. You don't know, right? Because the function might not just converge to any point when x approaches infinity. Is that correct? X just changed, right? The function just continue like this and never stop at any point. Does that make sense? So the limit of this function does not exist. Does that make sense? But the limit of the function limit of x sine x over x when x approaches infinity is x. And you can see 0 is the limit of sine of x over x. Why? Because we know exactly sine x over x is less than or equal to absolute of sine x over x. Or I can write, that is just, less than or equal to 1 over x. Does that make sense? And of course, this is greater than -1 over x. Is that correct? Because sine of x takes value between 1 and -1. Right? So that's why we have this. Then the limit of -1 over x and 1 over x at infinity is 0. We know the limit of -1 over x approaches infinity is 0. Why? That is less than the limit of sine x over x when x approaches infinity, less than the limit of 1 over x approaches infinity, and that is also 0. So by the squeeze theorem, the limit of our function is also 0. Right? So what does it mean? Look at this graph. And then you compare with the graph of sine, right? So you have this picture. This is x. This is y, 0. When x approaches positive infinity is right here. The function approaches 0. Okay? So, usually the sine look like this. Right? But for this function, when x increase, the amplitude is just decreasing to 0. Is that correct? The absolute of this function just increased to 0. The function may be negative, may be positive, right? Change from time to time, but you have the following picture. Does that make sense? So, this just closer to 0. I think I do something wrong in here because, when x equal to 0, the function should be 1. Okay, let me erase this. I'm sorry. We know the limit of this function at 0 is 1. So I think we have to start from this. Okay. Does that make sense? So, yeah, that's it. Again, right? Limits at some point equal to infinity gives you information about vertical asymptotes, and limit at infinity gives you information about horizontal asymptotes. And all these informations have to understand the function at some finite point and at infinity. So we finish our video in here. In the next video, we study how to graph a function. That means we will, compile all informations we know from the first derivative, from the second derivative, from limits of functions at a finite point at infinity, and then we will graph them. All right? See you.